We're going to take a look at solving this undamped free vibration problem in Octave using numerical methods. In order to solve the associated differential equation, we need to know the stiffness value and mass value. Both of these are calculated in this example problem, and the final differential equation is also formulated. We're going to directly use Octave to solve this equation. This differential equation is subject to these conditions. Displacement at 0 is 1/48 feet and velocity at t equals 0 is 0. Let's switch over to Octave. I already have a temp.m file set up. Let's create a function temp and then use unfunction syntax to enclose it. Now first we need to define our system of differential equations. We are going to define another nested function. df is a function of time and displacement, and when I hit enter it will automatically enclose the function. Now I'm going to define two variables, mass and stiffness, and let's see its value from the solutions. Mass is 31.06 and stiffness is 90625. Mass is 31.06 and k is 90625. Now I will define the differential equation itself, but before I do that I need to convert it into a form that Octave solver understands. The differential equation I'm trying to solve is of the form mu double dot plus ku equals 0, and to understand what's going to happen in the transformation process, let's add the subscript 1. Now let's substitute u2 equals u1 dot in this equation, and let's call this equation A. So this would imply that mu2 dot plus k u1 equals 0. Rearranging this equation for u2 dot, so u2 dot equals minus k by m u1. Let's name it equation B, and these are going to be the two equations we're gonna instruct Octave to solve. Let's head back to our Octave workspace and write the differential equation. The first equation, df of first equals u of 2 because it's the second derivative, and then second equation, df of 2 equals minus k by m times u of 1. As our system is set up, we're going to just solve the equation for t u equals ODE 45, close the bracket parenthesis. The first argument of ODE 45 requires a method pass. We already defined a method for differential equation, so at and then f, this function right here, comma. The second argument is the time range for which we want to calculate the solution. Let's define another variable for time range, t range equals 0 at a step of 0.001 to 0.5, and pass it to the ODE 45 function. Another argument is it requires initial conditions, so let's name it u naught and define the variable here. U naught equals, create an array, and the first element of this array is going to be the displacement boundary condition, and the second is going to be the velocity boundary condition. So first displacement boundary condition is 1/48 and velocity boundary condition is 0. At this point we already have the solution, so let me just plot it. Plot on x-axis we want the time, and y-axis I want displacement. So select all values of the first column in u displacement field and product, semicolon, save, and run the program using this play button. This is our required solution. Let's compare it with the solved example. Switching to the solved example, let's compare it with our solution. The waveform is matching, but if I look at the maximum amplitude, it is 0.02 and here it's 0.2. This is because here it's in inches and these are in feet by default. So let's change it. Let's close it first and switch to our workspace and multiply our displacements by 12. In this program now, we're gonna get correct answers. We switch back to the PDF and compare solution. It's exactly 0.2, same number of cycles, same maximum amplitude. This is 0.24.